Let's talk about WebSockets. So for the so just to give a roadmap of where we are on the homework, we did everything for Learning Objective 1 on Monday. What day is it? On Monday. You have everything you need to be able to do Learning Objective 1. Today we're going to cover everything for Learning Objective 2, which is actually using the WebSockets. Objective 1, Learning Objective 1 is just making the connection, establishing a connection between client and server that's going to be a WebSocket connection, basically using raw TCP for the communication. Now we're going to use it to send chat messages, which, no real sugarcoating it, Learning Objective 2 is a lot. There's a lot going on here. This is a big portion of this homework is Learning Objective 2. We're going to cover everything you need for that today and also for Application Objective 1. After today, you can get all the way through Application Objective 1 on Homework 3. So in 2 lectures, we're getting through the first 3 objectives. And then on Friday, it's more of a tips and tricks lecture. We're going to see WebSockets in action. I'm going to fire up a server. We're going to see some live data and just give you a better feel for how WebSockets work and some tips on how to work with them, how to code them, how to test them, things like that. Today we're going to finish all of the concepts, though, that you need. So any questions on that before we get into slides? Or are you all just still thinking about Homework 2? Yep. Yep. Yeah, so whenever I plan the schedule for a course, I treat spring break as a complete void in the schedule. So anything that would be due during spring break will be due the week after. So this isn't due the expected, well, actually this is due way after spring break, isn't it? But the Homework 2 actual deadline is the relevant one right now. That's not due till after break. Yeah. Right. Any other questions on anything? I'm not even going to limit it to whatever, to homework or whatever. Yeah.
What's the difference between
Yeah, good question. So what's the difference between what Socket.io does and what we're doing? Socket.io, for those of you who don't know, it's a WebSocket library. You import Socket.io and it does WebSockets for you. It does everything that we're doing on Homework 3, plus it adds the idea, it adds a few things. 2 of the most notable things is it handles reconnections gracefully. So if the connection is ever severed, it will reconnect automatically without you having to think about it or do any extra work, which we could put on the homework, but I don't see a need to do that. And it also introduces the idea of message types. We'll do this by communicating JSON strings, and then the JSON string will have a type, and then we'll just have a string for the type. Socket.io builds that into their protocol and has a type and then methods where you say, send a message of this type, and then here's the data. So it adds just a little bit of extra creature comforts, I guess, on top of the WebSocket library. But underneath the hood, it is WebSocket still. And generally, when you use WebSockets in practice, Socket.io is pretty much the go-to. It has libraries in any language that you'll reasonably want to use. Stuck on Homework 2, LO2. Pick shows on the page, but always broken. Yeah, Homework 2, I'd say Homework 2, LO2, and Homework 3, LO2. Both of those are, that's where it's really testing your both understanding of the concepts covered and your ability to write code that implements the protocols that we covered. And then the application objectives are adding extra features onto those things. It's the Learning Objective 2s, which Learning Objective 2, even on Homework 1, was hosting a site. Which by the way, I haven't taken the time out to talk about that this semester yet, but even from Homework 1, you started up a TCP connection, just a TCP connection, and you wrote code that's acting as a web server and hosted a website. No libraries, no imports or anything except the TCP stuff directly, and you built it. Like that's a cool accomplishment. Like you can build a web server. You don't need Django, Flask, HTTP libraries even. Why am I blanking on the one? Express. You don't need any of those libraries. You don't need any of those frameworks. You can just write this code yourself. And, I don't know. It's a really cool accomplishment, I think. Especially when we do WebSockets, and we're going to do authentication in Homework 4, which doing that from just a TCP socket, you really understand how the hell web servers work. So let's get into it. WebSockets. So last time we established a WebSocket connection and we did nothing with it. Establishing a WebSocket connection isn't useful if we're not communicating messages over that socket. So let's talk about how we're going to send messages back and forth, client to server. And luckily, just like HTTP, from client to server or server to client, the protocol is almost identical. It actually is we'll see, you'll see it. But it's pretty much the same exact structure, whether it's a message from the client to the server or from the server to the client. Just like an HTTP request is structured almost the same as an HTTP response. So we get to kind of double up on a lot of our knowledge on this one. And this is it. I could just show this slide and be done, right? This is the structure of what we call a WebSocket frame. So any message sent over a WebSocket is going to be sent in what's called a WebSocket frame, which has exactly this structure. So the actual information that you're sending is the payload down here. This is where your actual message will go. And then the rest are the headers, which are going to be the bits that we have to parse. So this is what we'll talk about all day today, is how to parse this. I obviously can't just show this picture and have you go code it up. Office hours would be quite busy. So let's talk about this, break it down piece by piece, and explain exactly what this thing means. First, we're going to take a little detour to talk about what context are we even talking about here. So the internet is, we kind of saw what the internet is. It's a bunch of wires connecting everything and then a little bit of wireless to connect your device to a network. And then we have several protocols to be able to make use of those wires. And the protocols are not magic at all. There's no magic at all involved with them. What a lot of these protocols do is just define what those ones and zeros mean. So when I get a bunch of ones and zeros over the network, what do those ones and zeros mean? And we saw TCP and IP as our first two examples of that, of how to make those ones and zeros make sense. So for an IP packet, the first 4 ones and zeros, the first 4 bits, are going to represent the IP version number for that packet. And then we have the IHL of the next 4 bits, and then et cetera, throughout this whole thing. So you get a bunch of bits, and it's all just ones and zeros, but those ones and zeros have meaning if we're following the protocol. And if every device on the internet, and in the case of IP, if each router and endpoint on the internet codes their software the same way according to the same protocol, then we can effectively communicate over the internet. When we send an IP packet, we follow this, and then when the routers read the IP packet, they read that, then we assign meaning to those ones and zeros. We assign meaning to the bits. It's going to be the same with WebSockets. We're assigning meaning to the bits. So we get these bits, and this is what you'll read when you call socket.receive or whatever language you're using to get your bytes off of the TCP socket. You're going to get your bytes, and you're going to use this protocol to make sense of the bytes that you receive, or the bits even that you receive. So when we have a WebSocket frame that's actually flying across the internet, that's flying through the air or going through the wires of the internet, we're actually going to use the network stack. Something I don't talk a lot about in this class. Take modern networking concepts if you're interested in this, if you want to learn a lot more about it. But the network stack, when one of these WebSocket frames is flying through the internet, this is actually what it's going to look like. It's going to have just a bunch of ones and zeros, and it's going to start with the IP headers, then the TCP headers, And then the content of the TCP headers, so the content of the IP packet is this whole thing. The content of the TCP packet is our WebSocket frame, and by the time the data gets to our software at the application layer of the network stack, the IP headers have been read and removed. Those are already gone. Our TCP library is going to read all these headers and remove those headers, and then we're just going to get the application layer bytes. So we're going to get just the WebSocket frame. But this is how our protocols of the internet work, is we send a bunch of ones and zeros over the internet and use these protocols to make the ones and zeros make sense. So everybody's following the same RFCs, the same protocols. That's the only thing that makes the internet work. If somebody says, you know what, I don't like these bits in this order, I'm going to put things in different order, their stuff doesn't work. Yep. So the plus and minuses and everything, that's just ASCII art. That's just their way of visualizing it. I don't know why the RFCs still visualize things like this, but that's just them making boxes. But this means the first bit, this is going to be the first bit, second bit, third bit, all the way up to the 32nd bit. And then the 33rd bit would be this one right here. So the 33rd bit will be the first bit of the identification. And the rest is just visuals. So we're concerned about just the WebSocket stuff. There's just our little detour there. But for the WebSocket stuff, this is what we're actually going to read. This is the only part of that packet that's going to hit your code that you're going to read from your TCP socket. By the way, the same is true from HTTP. The payload of the TCP sockets would just be HTTP requests and HTTP responses. All the rest is already stripped away. And then HTTP, instead of assigning values, meaning to the bits, HTTP said, parse these headers as a string, and the headers will tell you how to parse the rest. So it's very different when we're parsing HTTP compared to these three protocols. So it felt a lot different when we were doing that. Now that we're doing WebSockets, we have to make a little bit of meaning out of these things. All right, so let's parse some bits. We're at the bit parsing level of the course. Yes, I'm excited. So when you read this has been happening all semester, when you read your bytes from the TCP socket, what you're actually reading is an array of bytes. And it's useful to remember that a byte is an integer value between 0 and 255. It's 8 bits. If they're all ones, that's 255. If they're all zeros, it's 0. And then everything binary in between, counting in binary. So it's important to remember that your bytes are just 8 bits. That'll be helpful when parsing this stuff here. So reading individual bits, for example, the opcode, we want to read just the opcode of the first byte. We'll go through what each one of these means, but just a practice with bits here, because this is something a lot of you probably haven't done in code. You know all the concepts behind this, but not where it can apply. So let's talk about it a little bit. If you read from your TCP socket, you get an array of bytes. Each byte is 8 bits. This protocol, the way it's visually represented here, is 4 bytes wide. It's 32 bits wide. So if you read from your TCP socket and you're expecting it to be a WebSocket frame, and you read the byte at index 0, that's going to be this information right here. This is byte 0 out of your byte array when you read from your TCP socket. This will be the byte at index 1. It'll contain this information. The byte at index 2. The byte at index 3. The byte at index 4, etc. So visually, you should be thinking of this as a bunch of bytes that you can read, and then you can break those bytes into bits. So if you want to read the opcode, which is the 4 least significant bits of the first byte, you're going to read the first byte, the byte at index 0, after you read from the TCP socket. And then you have three different values that are sharing that byte. We have the fin bit, the reserve bits, and the opcode. If we just want to read the opcode, which is the 4 least significant bits of that byte, we can use what's called a bit mask. This is very common, something you'll want to use throughout homework 3. We use a bit mask. So we're going to use a bitwise AND, which is an ampersand in most languages. If you ever wondered why a logical AND we use 2 ampersands, it's because a single ampersand is reserved for our bitwise AND operator, our bitwise AND. Logical AND is 2 ampersands, bitwise AND is 1. If you used 1 ampersand instead of 2 ampersands and like 115, well, actually 115 is in Python now, so we don't have that issue. But the common issue is students use 1 ampersand instead of 2, which is a reasonable thing to do when you're first learning programming. Well, you just did a bitwise AND instead of a logical AND, and sometimes it does the same thing, the thing that you want, but a lot of times it won't. So this is a logical AND. So if we take our first byte and AND it with 15, this is where we have to remember how binary works a bit. If we AND it with 15, which is the value 00001111, then we'll effectively zero out the 4 higher order bits, and what's returned is just the opcode bits with the fin bit and the reserve bits zeroed out. So whatever we have is going to be the opcode as an int from 0 to 15. 15 if the opcode is 1111. If the opcode is 10 in decimal, it'll be 1010. So if we say, what's the opcode? Print the opcode after bitmasking it, ANDing it with 15, and 10 is printed to the screen. That means that you have an opcode of 1010. So you can use this integer to check what the opcode actually is. And I'm picking on opcode here, but that's your general procedure for extracting single individual bits out of a byte. You're going to mask them and then check what's returned after masking. Yeah. Oh, yeah, it'll use 32 or 64, I forget. But 15, when you AND it with the byte, you'll get the integer value that you're looking for. You're right, though. There might be a lot of extra leading zeros. You can, unless you represent 15 as a byte, if you create a byte with the value 15. I guess I don't specify the type here, so I can get away with that. If you create a byte with the value 15. But you'll get away with ints. Like if you create 15 as an int and AND it, you just have more leading zeros, so it's still going to return a value from 0 to 15. All right, and let's go through these bits. And to expand that example, if you want to extract just the fin bit, you'll read the first byte and AND it with 128. 128 is going to be a 1 followed by 7 zeros. So if you AND that byte with 128, it's going to mask out everything except the 8th most significant bit, which is going to be the fin bit. So all that Boolean stuff, you have to remember how that stuff works, which, again, that's what I get excited about. You actually get to use that knowledge. You learn that in other courses, and then you just kind of throw it away, and you never really use it in your career. If your career is going to touch WebSockets, you're still just going to use a library to do it for you. But just knowing that it's bits underneath the hood, that's what that library is doing for you, is avoiding your need to do bit parsing. Even that's, I think, useful knowledge to know. That's why you import that library. But somebody had to do the bits for you. And luckily, there's somebody out there who wrote all that code for you and then let you use their code for free without even crediting them. Which, not to get too sidetracked on that, but that's an incredible thing. In software in general, we have so much open source software. People spend countless hours writing this code, days, weeks, years even, teams of people. Let you use it for free. And you don't even have to say, when you publish a project, thank you, credit to the developers of the Python programming language for writing millions of lines of code and giving it to me for free. You don't even have to do that. It's a wild thing. I don't see that in any other industry. Absolutely crazy. And absolutely wonderful as well that exists in software engineering. And especially for for a field where the pay is so high that so many people are willing to give away their work for free it's incredible. There's no other word for it. Anyway, FinBit, 1 or 0. 1, if this is the last frame of a message. Like, imagine accountants doing that. Like, they would never, no other field, not just pick on them specifically, no other field does that. Lawyers going to give away their stuff for free? No effing way. So 1, if this is the last frame of a message, and 0, if it is not, if there are more frames in this single message. So if you read a message, a lot of the time until you get to application objective 1, the FinBit is going to be 1, and you'll just have 1 frame for a single message. But when you get to application objective 1, there will be cases, and we will test for situations where the FinBit is going to be 0, which means there are more frames coming for the same message. I'll talk about that a little more when we get deeper into this protocol. The reserve bits, RSV for reserve, this one's easy. They're always going to be 0. They're reserved for additions to the protocol. We're not going to use any additional protocols. We're going to just use plain old WebSockets. So reserve bits, always 0 for the homework. We don't have to think about them at all. You don't have to parse them. You don't have to read them if you don't want to. They're just always going to be 0 for our purposes. The opcode, this is going to be a 4-bit value, which is going to tell us what to expect from the payload of this frame. So what is the payload data? There are a couple that are going to be important to us. 0001, if the payload is text, which if there is a payload, it's going to be text in our cases. So we want to check, is the opcode 0001? 0010 for binary, which I don't make you do anything with binary on the homework, so really don't have to worry about that one on homework 3. But say you were sending an image with WebSockets. I had it as a bonus objective one semester, but I haven't had that in a while. If you want to send an image, upload an image via a WebSocket, which you can do, you don't have to use the multi-part form stuff. It's obviously much harder with WebSockets, but you could do it with a different opcode and then just send binary data over the WebSocket frame. Another one that we do have to care about is 1000. This means that it's a request to close the connection. The connection is about to be closed. So this happens if you have a tab open with a WebSocket connection and somebody closes the tab. The browser is going to send a close message, and then you should gracefully close that WebSocket connection on your server to make sure that that connection is removed from anything that you're doing with that WebSocket. And 0000, and you will see those, we will test for the closing in application objective 1 at least. We won't close connections for learning objective 2. And then 0000, again, only for application objective 1, not for learning objective 2. 0000 is a continuation frame. So if the first message, the FinBit is 0, saying this is not the last frame of a message, then at least the next frame, and until the end, the last frame, which will have a FinBit of 1, all the what we call continuation frames, all the frames after the first one in that single message are going to have an opcode of 0000. Only the first frame will have a non-0000 opcode. And of course, you can convert these to decimal for your code. If you want to do your mask bit and check if opcode equals 8, then it's a close request. You don't have to go always in binary. You can convert these to decimal and then check for those decimal integer values in your code, depending on what you favor in your code, what you want to do. The mask bit, it's either 1 or 0. It's only 1 bit, it has to only be 1 or 0. 1 means a mask is being used, and 0 means a mask is not being used. We don't know what a mask is yet. We'll talk about mask when we get to the masking key here. But if the mask bit is 1, that means this masking key exists, and these 4 bytes are going to be that masking key. And when we're reading messages from the client, the masking bit is always going to be 1, and the masking key will always exist. These 4 bytes will always be the masking key when you're reading frames from the client. When you're sending frames to the client, your masking bit will always be 0, and your masking key will not exist. I'll have more talk about that when we get to the masking key. But for now, the masking bit, 1 if the key exists, 0 if it doesn't. Payload length. This one's going to be a conversation, so let's talk about it. Payload length. It's very similar to content length, especially in the sense that this is telling you how many bytes to read of the payload. So all the conversation we had about buffering, that's going to apply here. And we're going to have a new conversation about reading multiple frames, multiple consecutive frames. So the payload length is telling you how much information to read from the payload data, which you can think of as the body of an HTTP request with content length. So how many bytes are in the payload data, and you have to buffer until you read that much information. But the extra thing is that you might have multiple frames being sent back to back. So when you're buffering, you might actually read more than payload length number of bytes from the payload, which means you've started to read the headers of the next frame. Remember, this is a continuous connection. It's a stream of data. So we're going to get multiple messages sent back and forth on the same connection, where HTTP, TCP connection, request, response, close TCP connection. So we never had this problem with HTTP, which we could reuse the connection, but we're not in this course. But with the WebSocket connection, we are reusing that connection. So if the client sends 2 messages very quickly, and they're large messages where you're buffering, you might read part of the next message while you're buffering for the previous message. So that's something you have to look out for. I might be able to spring up some examples on Friday. But other than that, I'm not going to talk about it too much. That's one of those things that you have to that you'll have to code around. So what is the payload length? How do we read this thing? Well, it's a little tricky, so let's talk about it. If the payload length is less than 126 bytes, so we have different scenarios here. If the payload length is less than 126 bytes, this is the payload length right here. 7 bits. It's going to share a byte with the masking bit, and these 7 bits, that's your payload length. Whatever those 7 bits say, that's it. That's your payload length, yeah. I think I said multiple. Scenarios, right? What did I say? Oh, maybe. I don't know. There are 3 scenarios, though. Thank you. So this is the payload length if the payload length is less than 126, and that's it. You read the payload length, and then all this stuff right here doesn't exist. The very next byte is the masking key. So you would go payload length in byte number 2, and then the masking key, the first byte of the masking key would be the 3rd byte, the byte at index 2. So that's our first scenario. The payload length is less than 126. That means the value fits in 7 bits, and we can represent the payload length in just those 7 bits. We don't need any more room to represent payload length, so we're not going to use it. Second scenario, the payload length is greater than or equal to 126, but less than 65K, or 64K? This number. I think that's 64K. Less than that value. This means that the payload length can't fit in 7 bits. I mean, it could if it's 126 or 127, but we're going to see why that can't work. That means the 7 bits is not enough to fit the payload length, and we're going to use 2 bytes to represent the payload length. So in this case, the 7-bit payload length is going to be exactly 126, or all ones and then 1 0. 6 ones and then 0. So payload length, if the payload length is exactly 126, the 7-bit payload length, that means the next 2 bytes are going to be your payload length. So you have to read the next 2 bytes and combine them into one larger int, which won't fit in a byte. So combine these 2 bytes into one int, that's your payload length. If the payload length is greater than 64K, then the payload length, the 7-bit payload length, will be exactly 127, and the next 8 bytes, this is a huge amount of information to store one int. the next 8 bytes, I guess we're used to 64-bit ints, but the next 64 bits is going to be your payload length. So all of this information will be used, all of this space will be used for the payload length. Whereas if this is 126, the next 2 bytes are the payload length, and then the masking key will be right here. When it's 127 for the 7-bit payload length, the next 8 bytes are used for payload length, and then the masking key is right here where it appears visually on the diagram. So your WebSocket Frame payloads can be on the order of exabytes. These things are like the people who wrote this protocol were looking at IPv4 and saying, we don't want to run into that same issue. We're going to make this future-proof. Even if somebody wants to send 16 exabytes, they can use a single frame for that. Now, in reality, you're going to split that into multiple frames anyway. The protocol has a way to send one single message in multiple frames with the continuation, with the fin bit and the continuation opcode. So I'm not sure why they went this far with it, but you can have WebSocket frames in the order of exabytes. Yeah. Yeah, I don't know. That's a good question. What's the point of a fin bit if you can have such large frames? I don't know why they had the need to do this, but this thing's future-proof. No matter what route we want to go, it's available to us. And honestly, having a fin bit of 0 would be the preferred option. If you want like streaming data, you want to say, hey, here's some data. I'm not done yet, but I'm going to send more, but here's some. You can process this right now. If you send a 16 exabyte frame, I got to buffer 16 exabytes before I can start processing this thing. It's not really feasible, but I don't know. They wanted to future-proof the thing, I guess. Maybe someday 16 exabytes will be a small number. I don't know. So your process when you're parsing the payload length is you're going to read this 7-bit payload length, and if that value is less than 126, then those 7 bits are your payload length. If the value is 126 exactly, read the next 2 bytes, that's your payload length. And if this value is 127 exactly, read the next 8 bytes, and that's your payload length. So we have 3 different scenarios. For application objective 1, we're going to test all 3 scenarios, making sure you handle all the payload length situations. That takes a bit of coding. That's where you spend a decent amount of time, is just parsing the payload length and writing your payload length. When you send a WebSocket frame, you have to generate your payload length following the same procedure in reverse. So be aware of that. This is a chat app, so you get a message and send a message, but since you have to escape your HTML in the messages that you receive, and the JSON format's a little bit different, the payload length will change. So what some students like to do is just try to borrow the payload length from what you were sent, but you do have to send things in slightly different formats that's going to change the length. So no cheese there. And we will test the boundaries where you get a message that's like 124 bytes and you have to send a message that's 130 bytes or something like that, where the scenario switches from what you receive to what you send. So just write your code to actually do that. We look for the cheese. So after all the payload length, however much room the payload length takes up, if the mask bit is 1, then the next 4 bytes will be the masking key. This will be 4 bytes of random crap. This will be randomly generated or somehow generated by the client, random to us. Will be generated by the client. It will be different every single time we get a frame. So you have to read these, you have to parse these. There's no way of getting around reading this masking key. This has to be read every single time. This is 4 bytes are going to be XORed with every 4 bytes of the payload. So the payload isn't just raw data. This isn't just your message, the message that's being sent. It's your message masked with the masking key. So the first byte of this payload is masked, XORed with the first byte of the masking key. The second byte of payload data, second byte of the masking key. Same with the third and fourth. And And then when we get to the 5th byte of payload data, that's again masked with the first byte of the masking key. So each 4 bytes is masked with this masking key by XORing the original message with the masking key and then sending the masked payload. So where's my why the hell do we do this? I guess I'll just say it right now. Why the hell do we do this? This is another cache busting thing. So if the client's sending us a message, we don't want that response to be cached in any way. I don't think anything should be caching WebSocket messages anyway, but if it wants to, we have this to bust that caching. Make sure that we actually get the messages that are being sent to us. What I recommend when you're parsing this is don't do this 4 bytes at a time. You're going to get an index out of bounds error 75% of the time when you do that, unless the payload length is divisible by 4. That's the only reason you're going to avoid that. So I would iterate over the payload data 1 byte at a time. Use a modulo operator to figure out which byte of the masking key I need to XOR it with, and then grab that byte from the masking key and then XOR it. So just a tip to avoid those index out of bounds. You used to see that a lot in office hours, so I give that tip. So suppose we have 4 bytes of the message. We have these 4 bytes. Before it's sent to us, the client is going to generate a random masking key. It's going to XOR these 2 values. So XOR 0 is 0, 1 XOR 1 is 0, XOR 0 and 1 is 1, etc. So we have those 2 values XORed together. And then when we receive the message, we're going to XOR the masked payload with the masking key again. So if we do 0, 0, XOR, that's 0, 1, 0, 0, we're going to get exactly the original message back. So if we take our message, XOR it with the masking key, then XOR it with the masking key again, the 2 XORs with the masking key just zero out completely, and then we end up with our original message again. So we can still recover our original message with XOR operators, but whenever it's sent over the internet, it's different each time. Even if somebody's spamming chat, it's going to be different every single time, so we can avoid caching. If anything is tempted to cache, this is going to prevent that. Once you demask the payload, at that point you're outside of the realm of WebSockets, and you can process that message however you're going to process it. For our cases, it's going to be a chat app. You're going to read a JSON string. You're going to parse the JSON string, store that chat message with the username your server generated for that client, store that in the database, and then go to every other WebSocket connection and broadcast, hey, everybody, this person said LOL in the chat. When you send, any questions so far, by the way? I haven't been looking at my phone. My phone fell asleep. You can go to Piazza or office hours. Yeah, I think they just wanted to vent a little. I don't think they were actually asking for help in chat. Yeah. Off the top of my head, I want to say no. Certain browsers do funny things. Especially Chromium browsers have a lot of little efficiency things built in that tend to break things. So Chromium browsers might want to close the connection. I don't know 100% on that. I'm just guessing. But it shouldn't do anything. Not until you actually close the tab or the window. Then it should send the connection closed message. But minimizing it shouldn't do anything. But Chromium always surprises me. I was fighting it with I think I mentioned this, but I was fighting Chromium with I was testing on Opera and Chrome. Neither of them would work with my Spotify extension, my browser extension. And my answer was to switch to Firefox, and now it works great. Because it was when I don't have the tab active, but I want my extension running, and it would shut down my extension because I wasn't actively on that tab. Even though that desktop is actively on the tab, since it doesn't have focus, it would put it to sleep and say, oh, the user isn't doing anything here. So it might do something similar with WebSockets. I don't know off the top of my head. It shouldn't, though. It's not supposed to. Google likes to break our stuff. So when we send frames, it's not a good idea to use the Unix. I was wondering, are you saying that's a good idea to use the Unix epic? Yeah, in case there's more than one client per unit of time. And is the Unix epic, that's not going to fill up your 32 bits either, right? Is it? Oh, it will these days, won't it? It should fill those up. Yeah, I wouldn't use that. I would use some pseudo random number generator. I don't know, whatever the browsers use. It's front-end stuff, so I don't have to think about it. So whenever you send a frame to your client, one of the nice things about WebSockets, exact same protocol. Same exact thing, you just run it in reverse. Instead of parsing, you're creating WebSocket frames and piecing together a byte array with all this information in the right spots, everything the way we expect it to be, and then send it to the client. WebSocket's the same if you're sending or receiving messages. There's one big difference, not with the protocol itself. The protocol is exactly the same. But the difference is when you're sending a message to the client, you have no concerns about caching. The client isn't going to cache a message that you're sending to them. It doesn't quite make sense. So we don't mask our messages that we send, which saves a little bit of work at the very least on your homework and processing power in general. But there's no need for it, so we don't do it. So your masking bit is always going to be 0, and your masking key doesn't exist when you're sending frames to the client. So you don't have to worry about what to generate for the random key. That's a conversation we don't have to have on the back-end side. That would be if we're developing browsers, we would have to think about that on the other side, or writing a WebSocket client in general. We would have to worry about that. In this class, all back-end stuff, we don't have to worry about it. Your masking bit will be 0, and the masking key won't exist. So whenever you're done, whatever your payload length is, whenever you're done with the bytes for your payload length, the very next byte is going to be the first byte of your payload, and it will be unmasked. It will be raw payload data after that. So for your homework, reserve bits, always 0. Opcode, there's only 3 different opcodes we're going to worry about. The mask bit's 0, masking key doesn't exist. Payload length, you'll spend quite a bit of time working on. Then your payload is appended to the end of all of it. Your payload length in reverse. Nice bit 0. I already said that slide. God. With large messages, I mentioned this a little bit, but I said I'll talk about it again later. Now is later. So with large messages, specifically speaking of Chromium, I think this is Chrome specific though. I don't think Opera does this. I haven't checked lately though. It might have started. I don't know. But when you're sending a WebSocket message that's greater than 131,000 bytes, which will certainly be in your payload length of 127 for the 7-bit and an 8-bit payload length, it will definitely be in that range. It's over 64K. But we will test with messages over 131,000 bytes. When you send a message over 131,000 bytes in Chrome, and this has been pretty consistent across different versions of Chrome, different operating systems, different students, TAs, myself. We've seen this pretty consistently. Once you hit 131,000 bytes, and we will test with this if that wasn't clear, it will break the message into multiple frames. So the first frame you get, the fin bit will be 0. And the fin bit will be 0 for each consecutive frame until you see a fin bit of 1, which means you have the last frame of that message. We'll probably, should I even say this, but we'll probably only test with two frames. So if you get a 0, the next one's going to be 1, a fin bit of 1. But if you get a fin bit of 0, that means there are multiple frames for a single message. And you can test this by getting 131,000 bytes in your Chrome message. If you have purely ASCII text, this is the same as sending a message that's greater than 131,000 characters long. So the fin bit will be 0 until the last frame, and the opcode will be 0 after the first frame. So the first frame will tell you what the opcode is, whether it's text or bytes. Text, it'll be text in our case. And then every frame after that will be zeros for the opcode to indicate a continuation frame. You already know what the type of the data is from the first frame, so there's no need to keep telling you, hey, this is text, hey, this is still text, hey, it's text still. It doesn't have to say that. So the opcode is continuation frame opcode. The payload length, when you read the payload length is only for that frame. So if you read one frame and the payload length is 131,000, you need to buffer till you read 131,000, and then check after you're done buffering to see if you've read the part of the next frame. Make sure you put that information in some separate place while you parse that frame, and then read that back. Go back to the extra bytes that you read, because that's part of the next frame. Start parsing that. That'll have its own payload length, and that payload length will be the payload data for just that frame. So if your first frame was 131,000 and your next frame is 20,000, your total message length across both frames is 151,000 bytes. So be aware of that. Don't read the payload length and think it's the combination of all of the frames, including the continuation frames, because that would be impossible to parse. You wouldn't know how to parse that. The whole point of the payload length and content length is to tell you when to stop buffering. If it's for all of the frames, you would need to know how that's distributed across the frames to know how many bytes the payload length takes to be able to properly buffer. It just wouldn't work. So the payload length is for individual frames. Plus, if you want to send more than, if you want to send 20 exabytes of data, you wouldn't be able to do it for whatever reason you want to send that. So parse every frame. When you have these continuation frames, parse every single frame and set their payloads aside after they're demasked payloads. Concatenate them all together, and then when you get that last one with the fin bit of 1, then parse that one, combine all of the payloads, and that's your entire message for that message with all the continuation frames. And then you can process that message, store it in your database, broadcast it to all your other clients. When you broadcast, you can send it in just a single stack frame. You don't have to do the same thing Chrome's doing with the 131,000.